Hey everyone, my name is Matt Jones. I'm Matt Compiles on GitHub and Twitter, and I'm a front-end practice lead at Seek Jobs in Australia. Today I'm going to talk to you about Vanilla Extract and how it works under the hood. For those who haven't seen it already, Vanilla Extract is a CSS and JS library that my team and I developed alongside our design system, Braid. Vanilla Extract allows you to author CSS style sheets in TypeScript by utilizing compile time evaluation. Its API is designed to be a minimal layer on top of CSS itself, just enough to give you scalability and type safety. It also has first-class theming utilities that generate type data structures of CSS variables. Vanilla also lets you build your own abstractions on top of the base set of APIs. It does all of this without shipping any runtime code to the browser, and it compiles all your CSS to static, highly cacheable CSS files. This is all provided via a plugin to your preferred bundler or framework. We currently support Webpack, Next.js, Gatsby, ESBuild, Vite, and Snowpack. But first, let's address what you're all thinking. Why build another CSS and JS library? In the early days of our design system, we were hitting the limits of CSS modules. TypeScript was giving us the confidence to refactor our core systems while continuing to ship value to our users. But this all broke down once we hit our styles. We'd created a theme set of utility styles to power all of our components, but this was getting harder and harder to maintain. We looked into existing CSS and JS solutions, and they made styling components really easy and quick. But we wanted to continue using our themed utility class system. It fit perfectly with our design system goal, which was to write less custom CSS overall. We were also uncomfortable with the runtime overhead of CSS and JS. Not because the existing solutions were slow, but because we didn't really need dynamic styling, so there was no reason to pay a performance penalty. Now, there were also some zero runtime CSS and JS libraries, but none of them allowed us to express our styling logic in the way we wanted to. Their use cases were limited due to relying on static analysis of the code. Now, outside of CSS and JS, Tailwind was a huge inspiration for us. It's an amazing example of how a pure CSS API can be incredibly powerful. But things like type safety are non-existent unless custom wrappers were written over the top of it. So we didn't want to stop writing style sheets altogether. We just wanted to be able to reference our styles as confidently as any other dependency. And we wanted confidence to maintain and refactor our styles over time. What we ultimately wanted was to bring the power of TypeScript to CSS. And this is what Vanilla Extract is. It lets you author static CSS files, but gives you the confidence and refactorability of TypeScript on top. And now we've got the boring stuff out of the way, let's talk about how it works. Vanilla Extract uses a technique we refer to as compile time evaluation. Simply put, compile time evaluation is executing your code during compilation rather than in the browser, leaving only the results in the bundle. Let's take a look at some examples to show you what I mean. Pretend the following code is your very basic web app. We have an add function that adds two numbers together. Then we console log the result of calling add with 1 and 2. Because both inputs are known at compile time, we could actually pre-evaluate the code, leaving just the log statement printing the number 3. The add function can also be removed completely because it's no longer used. In a world where all code was this simple, you could apply this technique to remove runtime costs from your code. So what would it look like if we apply this technique to a CSS and JS library? This example shows a super basic CSS and JS setup. We have a style function that accepts a style rule, things like color red or padding 8 pixels. It then creates a single CSS class to represent the rule, returning the identifier to the class. All the CSS that gets created is just appended to the top level CSS variable. After the style function is created, we call it to create some background styles. The red and blue background variables could then be assigned to an element's class name prop to reference their respective styles. After evaluation, we now have a string of all the generated CSS. We also still have our red and blue background variables, but now they just point to their respective class identifiers in the CSS. All the style logic has been stripped away. Okay, so this is pretty cool, but we still have a few problems. Firstly, what do we do with the generated CSS? It's not much use just storing it in a local variable. However, we'll come back to this. Our other problem is, how do we decide what code should be executed at compile time? It wouldn't make sense to evaluate all your application code at compile time, and automatically detecting what code can be evaluated is an incredibly difficult task. And believe me, smarter people have tried. And even if we could detect what code was safe to evaluate at compile time, we want to be able to guarantee that all CSS logic is executed during compilation. And this is where ES modules comes in. It turns out that they make the perfect compile time evaluation boundary. They have their own top level scope, which keeps you from accidentally mixing compile time and runtime scopes together. And they have statically known exports, which gives us a way to safely communicate with the runtime code that will execute in your browser. So which modules should we execute at compile time? This is where vanilla extracts .css.ts file comes into play. We use the .css.ts extension as a signal to the compiler that this module is safe to evaluate at compile time. But as it is still a valid TypeScript file extension, we get all the benefits of TypeScript out of the box. The same goes for any other tools you may have set up, like Prettier or ESLint. For anyone across React's experimental server components, this idea will seem very familiar, although I'm going to claim that they stole it from us. Let's break down how a basic vanilla extract.css.ts file gets transformed during compilation. In this file, we're exporting two styles, a container and a button style, remembering that the style function returns a string reference to the generated class name. After evaluating the file, we're just left with the two exports being directly assigned to their respective class name identifiers. But there's something new here. We've also injected an import to a CSS file. Now, this file doesn't actually exist on disk. Instead, we use a bundler feature commonly referred to as a virtual module. A virtual module is essentially a file that only exists in memory. This is implemented slightly differently depending on your bundler of choice. However, an easy way to think about it is when the bundler tries to find the file, it broadcasts a message to its plugins asking if anyone knows about the file. At this point, Vanilla jumps up and says, "I know what this is," and hands over the CSS that we generated while evaluating the file. At this point, the bundler has everything it needs to continue compiling your application. All your styling code has been stripped away, leaving only the values you exported from the file. And we've also linked a virtual CSS file containing all the CSS that was generated. Your bundler can now handle this like any other CSS import, running it through post-CSS, minifying it, or merging it with other CSS files. Now, there are a few limitations to this approach. Firstly, as each .css.ts file is executed in isolation from the rest of your code, you can't reference any global state or perform any side effects. Secondly, all exports from this module must be serializable to JSON. This means you can't export functions from .css.ts files. If you do accidentally export something that can't be serialized, you'll receive a compiler error. So now we know how compile time evaluation can be applied, and we have our basic vanilla extract style function. What interesting things can we do with it? Here we have a React component, and it's supporting the mycolors export from the styles.css.ts file. MyColors is an array, so we're mapping over it and rendering a div with a corresponding class name for each item in the array. We're also importing some global layout styles just to make our demo pretty. Inside the styles.css.ts file, the mycolors export is sent to an empty array, hence why we don't see anything in the browser yet. Now we also have a colors.ts file. This is where we're defining our color palette, which is an object mapping color names to hex codes. This one is actually the excellent Tailwind color palette. Back in our styles file, we can import the colors from our palette and map over our color entries, returning a new style for each one. We can then set the background to the hex code and set the content property of the after pseudo element to the name of each color. And now we have a great rendering of each color in our color palette. Opening up DevTools shows us that all the styles we just created show up as a regular CSS class in a static CSS file. You'll also notice that the classes all start with styles_mycolors, followed by a unique hash. This is a debug experience to help you find where your styles originated from. In this case, from the styles file and the my colors variable. In a production build, each class would be identified by just the hash. Now looking at our styles file that was sent to the browser, we just see a statically defined array, pre-populated with all of our class identifiers. None of our actual styling logic was even sent to the browser. The import you see is the virtual CSS import that we spoke about earlier. Now, some of our color names are a little hard to read. It would be great if we could tweak the text color to ensure that they satisfy accessible contrast ratios. The readable color function from the polish style utility library can sort that out for us. It can choose the text color, either black or white, which best suits the passed in background color. After setting the color property, our color name should be accessible to read regardless of the background color. Opening up DevTools again, we can see the accessible text colors have been added to each class. And looking at the styles file in the browser, we can see that nothing has changed. Our accessible text logic all ran at compile time, so there's no need to bloat our bundle with extra libraries or run extra startup code before rendering something to the user. So now we've seen what can be done with the basic style function, let's take a look at what other features Vanilla Extract adds to our CSS development. CSS variables are a feature of CSS that benefit greatly from Vanilla Extract's TypeScript first approach. For those who haven't worked with CSS vars yet, they allow you to set custom variables in your CSS and then read the current value of that var in another style. To do this, you use the var function-like syntax you can see here. The best part is that CSS variables are only set for the children of the DOM element that you apply them to. They are effectively React context for your style sheet. Now this unlocks lots of possibilities for static CSS, but like the rest of CSS, they are globally scoped and there's no type safety. So obviously, Vanilla wants to fix this for you. Here we're importing the create var API from Vanilla Extract. This function creates a unique CSS variable identifier for you. This allows for local scoping of CSS vars, ensuring another team member on your project doesn't also create a different var named something generic, like background color. In this example, the background color variable is set to a string pre-wrapped in the var function syntax, so it's ready to be used in any style. But before we use the var in a style, we should give it a value. Here we're using Vanilla's global style API. It's similar to the regular style function, but allows passing in a raw selector rather than returning a class identifier. Using the root selector, we can set the var to red for the whole document. You'll also notice the vars key our property is nested within. This tells Vanilla that you're giving it a CSS variable reference and it will automatically unwrap the var function syntax in the string. Now we can use our variable in any styles we like. Often when using CSS variables, we use them in groups. We might be building a component that has multiple different color schemes and we want to declare our component theme as a contract of CSS vars. In this example, we're using Vanilla Extract's create theme API to define a critical theme for our component. Within the colors key, we've declared two variables, background and text. Vanilla allows you to create as many layers of nesting as you want when defining themes. Under the hood, create theme will call into the create var API for each of the defined variables. Create theme returns two values, a class identifier, so we can apply this theme in the DOM via an element's class name prop. We've named this one critical theme, and a vars object containing references to our locally scoped CSS variables. We can now consume these variables inside our root style. Okay, so what if we wanted to add a new promotional theme with different colors? We can use create theme again, but this time we'll pass in the existing vars alongside the values for our promo theme. This tells Vanilla that you're creating a variant of an existing theme and that it should reuse the variables from it rather than creating new ones. So now we want to wire our style and themes up to our component. Because we only want to apply a single theme at a time, let's export them as a theme lookup object. Now in our component file, we can use the theme import as the point of truth for the theme prop type, only allowing existing themes to be requested. This is also great because if we ever did add any new themes, we won't need to update our component code. After that, rendering the requested theme class name becomes a simple object lookup. All right, so now we've decided we want the critical theme to have larger padding. We'll add the padding to our theme and update our static padding value to use our new padding variable. But we've actually missed something here. We've added a new variable to our theme contract, but we forgot to implement it in our promo theme. This causes a type error, as vanilla extract won't allow incomplete themes to be created. This saves you from shipping a broken variant of your component. So by now, I hope you can see some of the benefits that vanilla extract brings to writing CSS. But what if we wanted to take things to the next level with our CSS APIs? Being able to export JSON data structures is great, but it can only take us so far when it comes to creating reusable abstractions. So remember before when I said that we can't export functions from .css.ts files? Well, that wasn't completely true. Let's imagine we wanted to create a declarative flex API. We could pass in props at runtime, like direction for example, and receive a valid class name in return. If you tried to do this, you'd receive a compile error informing you that you tried to export an invalid type from your .css.ts file. Now here is a refactored version of the same code. We've moved all of our logic into a create flex function. This then returns another function which owns the logic of deciding which class identifiers to return. I want you to observe how we've split our logic into two separate parts. One that runs at compile time and creates our styles, and another that performs our runtime logic. Let's pull our runtime logic into a separate file. We'll call this create flex runtime. Now we have the exact same result as before, but we've completely separated our compile time logic from our runtime logic. This allows us to import vanilla extract's add function serializer API. This API allows us to add instructions about how to replay a function when it is exported from a .css.ts file. The instructions needed are where to import the runtime logic for this function, in this case from the create flex runtime file, and what arguments should be passed to the function. In this case, it's our flex styles. The vanilla extract plugin can then read these instructions and apply them when generating the final styles file. And this is what the result of this process would look like in your bundle. We're importing the runtime portion of our Flex API and passing our generated class references to it. This approach also leaves TypeScript blissfully unaware of the compile time runtime boundary between the modules. Types can flow through just like any other function. Okay, so this seems like a very complex way to just export a function, right? You wouldn't want to be writing function serialization all over your code base. And I agree. The point of this API is to enable library authors to create powerful APIs that could still generate static CSS, but with the dev experience of a runtime CSS and JS library. You definitely don't need to understand how function serialization works to make use of vanilla extract. All right, so now we can export functions from our .css.ts files. How can we make use of them? One of the biggest hits in the CSS and JS space over the last while is the amazing Stitches. Stitches is a CSS and JS library that uses a variant-based API for creating component styles. Instead of thinking about styles in isolation, it encourages you to write styles that map to all the variant states your component can be rendered in. This allows you to define all your component styling logic upfront inside the styles themselves. It also generates a typed API to ensure your runtime usage is working as expected. If you haven't seen Stitches before, I highly suggest taking a look. The modules team does incredible work. So what would the Stitches API look like if we implemented it on top of vanilla extract? It turns out the approach of defining all your styles up front fits perfectly. This is the vanilla extract recipe API. It's available through the @vanilla_extract/recipes package. And just like Stitches, it allows you to describe component styles in all its variant states. Here we're describing the visuals of a button. First, via the base key, you can set your default styles in your component that are always present. Then you can describe all of your variant states. Here we have color and size variants, plus a Boolean variant named rounded. You can also set which variants should be enabled by default via the default variants key. Then there's compound variants. These allow you to express styles that are enabled by having multiple variants enabled at once. And of course, you can use the full vanilla extract theming API hand in hand with all of the styles in your recipe definition. Once you've defined your styles, it returns you a typed function that returns the required class list to render your component in that state. Over in our component file, we can render different variations of our button by passing in different combinations of our defined variants. As with all vanilla extract APIs, all your styles are created at compile time, and only the minimum required logic to return the relevant class list is actually sent to the browser. Currently, this API only comes in a function form. However, as React components are functions themselves, building a version that returns React components directly is entirely possible. Now, the final API I'm going to show you today is the aptly named Sprinkles. Sprinkles is an API that we could only have dreamed of in those early days of building our design system. It allows you to quickly create a set of themed utility classes via configuration. It then returns you a typed API for accessing them. You can think of this as a way to create a custom typed version of Tailwind or styled system. To get set up, first we call the define properties function. Define properties allows us to configure a collection of utility classes. The properties key allows you to pass scales of values to specific properties. A scale is a semantic mapping of named keys to values. For example, here our space scale has small, medium, and large keys, and they all point to specific pixel values. We can then expose our space scale via the padding and margin properties. To make things even more interesting, we can swap out our hard-coded space scale for a vanilla extract theme contract. The conditions key allows you to pass a set of conditions your property should be available over. This is normally to allow for responsive values or color scheme preferences via media queries. However, you can pass any valid CSS selector for more advanced setups. Scrolling down a bit, you can see that we're calling define properties multiple times. This allows us to set up different sets of conditions for different types of properties. Here our layout styles have screen width conditions, whereas our color properties are conditional via the user's preferred color scheme. To output our sprinkles function, we then pass all of our properties to create sprinkles. Now over in our component, we can call our sprinkles function to style an element. The type given to the sprinkles function ensures only valid properties are requested, and you get excellent developer feedback via the autocomplete. On this element, we're asking for a medium border radius and massive branded font on all screen sizes. Padding is using the conditional syntax to grow as the screen's width grows larger. You can see this in the mobile, tablet, and desktop responsive condition values. And our background and text color properties change depending on the user's light or dark mode preference. Here we can see the same code rendered across all three breakpoints and toggling our preferred color scheme, with dark preferences being on top. Opening up DevTools, we can see a huge list of utility classes have been assigned to the element. In production, this will be much shorter, as the debug information will be stripped away from the class identifiers. Having a look at the output CSS style sheet, it is filled with utility classes generated by Sprinkles. This may seem like a lot when you're first starting out, but if well configured, allows extremely high reuse of your CSS. Also note, as vanilla generates consecutive class identifier hashes, it compresses amazingly well due to such a high degree of repetition. We found Sprinkles to be an invaluable tool for building design systems with. Now that was a really quick run through of both recipes and Sprinkles. I have no doubt you could do a full talk on both of those APIs, so feel free to ask any questions afterwards to help fill in the blanks, or check out the docs. Just to recap, both recipes and Sprinkles are built using vanilla extract style API and use function serialization to create mixed compile time and runtime based APIs. They are both available via separate packages and don't rely on any private or hidden vanilla extract features. I'm super interested to see the community come up with other API ideas to build on top of Vanilla Extract's platform. So we've covered a lot about how Vanilla Extract works and what it can do today. We went through how Vanilla Extract evaluates your code at compile time and creates static style sheets, how theme contracts can make working with CSS variables scalable in large code bases, and how function serialization can be used to create excellent developer experiences, but still only ship the minimum required JavaScript to achieve it. If you enjoyed the talk and you want to hear more about Vanilla Extract, you can follow me on Twitter @MattCompiles, Also, please check out our doc site, vanillaextract.style, where you'll also find the link to our community Discord. Thanks very much for listening.